Okay, so as I said, today's going to be a big session on all of the harder parts of Mod 6. The way we'll structure it is it's going to be content. We'll do a very quick overview of the content because most of you probably have it by now, and we'll do more of our learning through questions. So we'll start through titration. We'll explain titration from front to back on these curves because I think a lot of people still struggle with structuring responses at this time of year. We'll then talk about Ka, Kb, pKa, and pKb, and how you can convert between them in the context of a question. We'll talk about back titration, how that all works, and we'll go through a practice question with this as well. And at the very end, we'll talk about buffers and how you can discuss buffers, but also perform a buffer calculation. So a fair bit to get through today. And what I'll do for those of you who are here, I'll send the notes for today into the chat. I've just put together the parts that we'll talk through, and we usually don't do this, but I think it's worthwhile sharing with you guys as you've made the time out of your day to spend on Sunday afternoon, probably pretty close to your exams. The notes are in the chat now. Okay, let's get started. So first thing today.
Oh, give me a second.
Oh, all good, Katie? Okay, cool. So the first thing we'll go through today is explaining titration. As you've seen now, there are pretty much 6 main curves you're required to explain in titration. The top 6 here, where you're reacting a strong acid with a strong base, a strong acid with a weak base, and a weak acid with a strong base. These are your 6 curves that are specifically stated in the syllabus you have to know. The bottom 2, weak acid, weak base, you may just want to know this if you're going for like, band 6, high band 6 to be sure, but there's nothing that says in the syllabus you have to know these. So what we'll do to go through this together, I won't just read through all of these. We're going to work through one together from our question bank. So it's all the way on page down below. I'll have to find the page quickly. There it is. Page 225 is what we'll talk through. Okay. So this titration curve, when you're writing any titration response and they ask you to explain a curve, say, for example, the question is explain the shape of this titration curve, 4 marks. Where do the 4 marks go? And I'll throw it over to you guys to take me through. Where could you get the first of 4 marks? Don't be shy. Unmute. Say in the chat. Starting pH. Cool. So what? That'll be first one. Second one, good RIN. It's going to be the equivalence point. That's a second of 4. What else? Mentioning whether they're strong, weak acid bases. Yes. So that would be mixed in with the starting point. And maybe you're talking about what happens beyond there as well. So the last thing you'll discuss is the ending pH, good RIN, acidic nature of salt. We'll talk on that with the equivalence point in a second. So acidic nature of salt. And there's one more important point we're missing. There will be a recording after. Yes, the shape, sort of, but more specific. More specific. There's one part of the curve we haven't talked about. Good. I see buffer region coming through now. That's what we're really concerned about. It's all of this portion, which is what we refer to as the buffer region. And this is what a lot of students will neglect in their titration curve explanations. So the most important thing in any titration curve before you start writing is that you need to pinpoint all the things you want to talk about before you even begin. So on this curve, if we were to talk through point number 1, how do we explain why the pH is 11 at 0 volume, 0 mils of titrant added? Why is it pH 11? And if we unmute, we go. Yep. We've got a mix of strong or weak base. Is it strong or weak? It is actually going to be a weak base in this case. And the reason we know that is because our pH is around 11, which is not particularly high. And again, afterwards, you see this shape of the curve where you have a sharp descent. That is very typical of a weak base being neutralized off. So it's a weak base. And if you were to write this response, it's a weak base because, or weak base accounts for pH of 11 initially being not as high as a strong base or something to this effect would be. And the reason is because HA only dissociates partially. In this case, the base only dissociates partially. NH3, in this case, will react with water.
Hopping upregulated.
To make NH4 plus OH minus. So you're saying that this will only dissociate partially, which means that your concentration of hydroxide initially isn't very high. And that's why your pH doesn't start very high. So only partial dissociation. Okay. This second part of the curve where we have a sharp descent, anyone know the reason why this would decline so sharply? Why does the pH decline sharply from pH 11 to 10? Good. Ashley's on the money. So if you wanted to go extra band 6 level, you're saying that there's a sharp decline because the free H plus in solution, free OH minus in this case, because it's a base curve. Free OH minus is being neutralized, and hence pH drops sharply initially. Okay. Because that's not what we see in the buffer region. Why does the pH now start to flatten out through the buffer region? How do we explain this? Not common ion. I wouldn't say common ion effect. Good. It's the buffer. So buffer has now started to kick in. So when you're adding in your H plus, you're reacting off OH minus, H plus plus OH minus is turning into H2O. And that is going to be reacting off any of the OH minus that is present in the solution. And if that's the case, you'd expect pH to start dropping sharply, but instead it flattens out. So how is the pH change being resisted by this buffer? It's being resisted because when you react off the OH minus, your NH3 is going to be shifted to the right to reform that hydroxide, reform ammonia, and be consumed. So the overall effect is that the hydroxide concentration and H plus concentration is relatively unchanged due to the resistance from the NH3 NH4 plus buffer. And that is why the curve then flattens out through this buffer region rather than continuing to drop sharply. Okay. Point number 3, equivalence point. This is the point where we have what? What is equivalence point actually defined as? Yeah, every mole of hydroxide reacting with every mole of H plus. Good. So we have equal amounts of acid and base at this point, and it's also known as point of complete neutralization. Point of complete neutralization is your equivalence point. Good, Sophie. The second thing to explain here, beyond the fact that it's got this sharp decline, why is the pH 5? I think someone mentioned it's an acidic salt, but how do we know it's going to be an acidic salt? How do we know this is going to be an acidic salt? Conjugates, strong acid, weak base titration, yes. Okay, weak conjugate base, not quite. We're getting to the right terminology. Yes, we know that it is acidic because the pH is below 7, but why is it acidic is my question. Why is it actually acidic in terms of conjugates? In this titration, we have a strong acid reacting with a weak base. And because of the conjugates, you will form from the strong acid a very weak base, and from the weak base, you will form a weak acid. Since conjugate pairs are weak pairing with weak and strong pairing with very weak. And that means that the product salt that you're creating overall has a weak acid and a very weak base. And very weak base is like virtually neutral. Virtually neutral, which means that overall, this whole salt should be an acidic salt, which is why your pH at equivalence is a little bit below 7. And that's something you should be able to explain for each of your curves. Why is equivalence above, at 7, or below 7? Okay, and the final thing, point 4, we drop to a pH of about 1.5, and this is likely because we have that strong acid which fully dissociates. And if you wanted, you can include a equation, show that complete dissociation. Going like so. Therefore, pH ends up low. Around 1.5. Okay. So for 4 marks, this is everything you possibly could write for this curve. Do you have to write everything here? No. But should you have something for each of these 4 points along the way? Absolutely. And if it's 4 marks, you should be thinking of 4 unique things to describe or explain through your response. And the big takeaway for titration is think about what you write before you explain the curve. Any questions there? Okay. Does the length of the buffer region impact anything? It just means that there's more buffer present. So if the buffer region was to extend for longer before you have the drop off, it means you just have more, in this case, base present to begin with. How do you know when to use reversible and irreversible arrows? You know to use one-way arrows in neutralization or strong acid-base dissociation. So a single arrow is neutralization or strong acid, strong base dissociations. And a reversible arrow is going to be in weak acid, weak base dissociation. In the context of mod 6. Those are mostly the rules. No, do not write over your graph in the exam. You'll write this on line paper, but just to show you what I'm talking about very directly on the graph, I'm writing over my graph. In your exam, write using subheadings where you talk about, for example, 0 mils, and then you write your stuff describing what happens at 0 mils. You might go 0 to 25 mils, and then write your lines describing what happens there. And then at 25 mils, you talk about equivalence point, and then at 25 mils onwards, you then continue on to write like that. Do we need to say anything about NH4 being a more clunky ion? No, that'd be for conductivity titration. If you're discussing a conductivity curve or graph, yes, you would talk about that. Does it matter in what order? No, but yes, I would say that if you can choose to do it in the chronological order, it's always better. So I would follow that. It's just easier to follow. Do we use Le Chatelier's principle to explain how the buffer works during the region of the curve? If you want to be thorough, yes. Anytime you reason a buffer working, LCP is part of the explanation. It's just that it's not probably not the focus of what they want you to talk about in a 4-mark response. So you've just got to be clever with your time. If you wanted to include it, you're not going to get marked down. If you're asked to explain a buffer normally for a 3-mark, 4-mark buffer question, you're going to talk about LCP, no matter what. But in this case, there's probably not enough marks to justify going that extra step unless you have time. Okay, cool. So titration curves. More in the notes view if you want to go through the rest, but we'll move on to Ka, Kb, pKa, pKb. The main thing I want you to take away from what these are is basically what do they actually measure and how can you convert between them? So what does Ka, Kb, pKa, pKb, what does it measure? What does it actually measure? And also, if this is helpful, just so I have an indication of speed, can everyone type like faster, slower, more in depth? Any feedback that you want to change in the way I teach, I'll just take it in and go on. More in depth? Can try. Okay. So yes, this is all about strength of dissociation, how much an acid dissociates, degree of ionization, strength, degree of ionization. Great. And you should know for Ka, Kb, pKa, pKb, what each of those would represent. So if you had a very large value for Ka, is this representing a strong or weak acid? Strong, good. And if you have a much smaller number, like 0.001, that's then representing a weak acid. So you should have that relationship where the turning point of strength for Ka and Kb is around 1. Anything much larger than 1 is strong, anything much smaller than 1 is weak. What's the turning point for pKa and pKb? What would make a strong acid or weak acid for pKa? Low pKa, small pKa, not quite. I think some of us might be mixing up with pH because pH would give you an indication of strength, but it's not to do with the number 7. pKa. Okay, what if we had a pKa of -50? Is that a strong or weak acid? Yeah, good Connor, good Zach. It's a strong acid. And if we instead have a pKa of positive 50, we know that is a weak acid. So Ka and Kb, pKa and pKb, they all measure strength. Ka and Kb are centered on 1. Bigger than 1, less than 1 is the difference. Whereas pKa and pKb, as we know, should be centered around 0. So if it's a negative pKa or negative pKb, that suggests a strong acid. And you can try this in your calculator if you don't believe me. Try convert a Ka of 1000 into a pKa. Tell me what you get. And for a weak acid, it's the opposite. If you have a positive number, it's suggestive that it's a weak acid. pKa, can it be 0? Yes, it should be able to. If you have a, I think it's if you have a pH, sorry, a Ka of 1, negative log 1, yeah. So if you have negative log 1, that would be where you have a pKa of 0. Any questions there to start? What pKa, pKb, and Ka-Kb actually are? No questions? Okay. So then how do we convert between them? The easiest way is to think of it as a box. Ka, Kb, pKa, pKb, and you can convert across any of these arrows. So to go from Ka to Kb, you know that Ka times Kb is equal to 1 times 10 to the negative 14. So you can manipulate that to change between them. You know that Ka is equal to negative log, 10 to the negative pKa, or pKa is equal to negative log of Ka. Same thing for Kb, except swap out Ka with Kb. And then between pKa and pKb, it's pKa plus pKb is equal to 14. And if you have these this square, converting between them is easy. So you can always go from any of these 4 to any of the other 4 using these operations. Okay. I think that's more or less what I wanted to talk on there. Here are those equations again that I've just mentioned. And we may come back to a pKb question at the end if we have time, but I think this is not as complicated as the other stuff we'll talk about today. Okay. Cool. So back titration, and AJ, I'm not sure if I understand your question. So if you rephrase it slightly, maybe I'll come back to it. Back titration. We'll talk about what it is, and then I'll give you a question to try, and then we'll see how we go. Back titration is a process where you have a acid or base that isn't particularly soluble usually. So you're trying to figure out how much of, usually it's going to be what's in here as the limiting reagent. You have an acid or base that doesn't really dissolve that well. So a very common example is aspirin. Aspirin tablets don't dissolve particularly well. And so it's not a good idea to try and make a primary standard from aspirin because it won't dissolve completely and you'll have an inaccurate measure of concentration. So a better approach is something that is not very soluble, is to use instead back titration, where you're placing a limited amount of the substance, the acid or base that isn't very soluble, and you're placing it into an excess to be neutralized. So here, if we only had 6 acid molecules and we placed in a known amount of base, an excess, here we have 9 base molecules, you have 3 excess, all of this acid base would get neutralized off, leaving behind an excess of base, an excess of base. And that excess of base is what you actually titrate in a back titration. So then you would perform a separate titration using some other acid to then find out how much excess base you had after the neutralization occurred. The reason why you do that is because if you know how much base was excess and you know the total base that you started with, you can perform the calculation that the amount of base that reacted is equal to the total base minus the excess base. And that would allow you to then find how much you reacted, which is these moles, the reacted moles. And that will go back to tell you how much acid was present in the first place, hence back titration. That's a quick overview. I'll let you loose on a question. Picked one out from the compendium. So we'll try page 213. Oh no, we'll do 182, sorry. Okay. So, hang on. No, we'll do this one. Sorry. Okay, 6 marks. I'll let you all have a go. I'll put 8 minutes on the clock. I know it's very time intense, but see how far you can get in. And for the Catalyst students who've already done this one, try page 182, question 29. So for the Catalyst students, page 182. For some of you may have done this already. Okay, 8 minutes on the clock. Have a go. Question in the chat, are all these excess values measured in moles? Yes. So you want to turn things into moles when you're trying to figure out how much is left over. And you can always send this back to concentration after. Dylan, I'll send the notes in the chat again for you. Just a moment. And if you have any other questions, feel free to put them in the chat while we work through this question. 3 minutes left. If you have the answer, type it in the chat. And if you're not sure where to begin, always start from the back of the question statement of back titration. So work from the titers, try to get some information from here, and then progressively move back towards the start. Okay, cool. Let's run through it. So I think we've got one correct answer in the chat from what I can see. The answer is approximately 64% to 2 sig figs. So if you got it, well done, Saf. But let's talk through how we get it. Saf, if you don't mind, are you okay to unmute and talk through it together? Are you good? Fair enough. Okay. So let's go through. Essentially, what you have here is a back titration where you have magnesium oxide as 2.65 grams, or a tablet that has that. Then you have 50 mils, 2 mole per liter hydrochloric acid, and the reaction mixture was then diluted with water to 250 mils. So we want to keep in mind we've got a 5 times dilution, which has happened here. We then have 3 samples of that 250 mils. So we've taken an aliquot, which would have the same concentration, and we've titrated against 0.1 mole per liter of sodium hydroxide using phenolphthalein indicator. The titer is shown, or 3 titers are shown, and you can look at the top one that is quite different to the other 3, or the other 2, sorry. So this is a rough titration. And whenever you see this, such a big difference between titers, you will always want to exclude something that is completely non-concordant. So in this method, we're going to take our working just from the second and third titration, even though we typically want 3. So the average titer, volume of the average titer is going to be 15.45 as the average of those. And you'll keep on working through. You know that you have used 0.1 mole per liter of sodium hydroxide. So you can then find the moles of NaOH, which is equal to 0.01545 liters times by 0.1, giving you 0.01545 moles of sodium hydroxide to neutralize what's in the 25 ml sample. Okay. An equation is probably going to help us. Anyone got the equation? Quickly read it out or type it out. GO. Hang on, sorry, wrong thing. And HCl. Yeah, HCl and NaOH is going to give us NaCl plus H2O. So this is a 1-to-1 ratio. Great, thanks, Seth. We'll use a second equation in a sec. And so you therefore know that the moles of HCl in the 25 ml aliquot is equal to the same thing, 0.001545 moles, since you have a 1-to-1 ratio. Any questions up to here? Okay, cool. So then using that, you can now find out the concentration of HCl in the 25 ml aliquot being equal to 0.001545 on 0.025. 0.001545 divided by 0.025, which ends up giving you 0.0618 moles per liter. And that's going to be the same concentration of HCl in the 250 ml volumetric flask. Since you only took an aliquot from it. Now to find the HCl left over from the initial 50 mils, you can now multiply this by 5 to reverse the dilution. So it's 0.0618 times 5 to give you 0.309 mole per liter. And you can find now the moles of hydrochloric acid you had present. Question in the chat, if it's C1V1 equals C2V2, then shouldn't N1 equal N2? As in the moles in the 250 mils, is that what you mean, Jess? Yeah, that's actually true. It would be the same. So you could save a bit of time and just do that. And you would end up having the same moles in the 250 mil as in the 50 mil sample, if that's what you were talking about. Is that right, Jess? Yeah, cool. Okay. But if we're here and we've already got the concentration of HCl excess in the 50 mils, we can turn that into moles anyway. So the moles of HCl excess is equal to 0.309 mole per liter times by 0.05 liters, since that's the volume it's contained in. And answer times by 0.05 is equal to 0.01545 moles. Of HCl excess. Now we can find the moles of HCl total because we were given the concentration and volume of the far in excess HCl. So 0.05 liters times by 2 mole per liter is equal to 0.1. And so the moles of HCl reacted is equal to the total minus the excess, which is equal to 0.1 minus 0.01545. And that gives 0.08455 moles of HCl reacted. Okay, any questions there? Always get confused in the dilution calcs in back and normal titration. Any tips? I would just say whenever you go through your stem, as you see a dilution happen, just label it. And so you know exactly what has happened. If you know there's a 5 times dilution, to reverse it, you're going to have to multiply concentration by 5. So I would say the key thing is just flag it if you see it. That way you won't forget. Okay, so we have the moles of HCl reacted, and then now we're going to take SAS equation from before for magnesium oxide, because this HCl reacted with the magnesium oxide originally. Magnesium oxide and HCl will form MgCl2 plus H2O, and that is balanced. So therefore, the moles of MgO reacted is equal to half the moles of HCl reacted, since it's a 2-to-1 ratio. 0.8455 on 2 is equal to 0.042275 moles. And to find the concentration, or do we need to find concentration? Yes, they ask us to find the percentage purity in 2.65 grams. So the last thing we need to do is to turn this into a mass by multiplying by molar mass. So excuse the extended working. The mass of magnesium oxide we have is 0.042275 times by 24.31 plus 16 for the molar mass of magnesium oxide. And that's going to give us 24.31 plus 16, 1.704105 grams, being sure to keep your numbers exact through your working. And to find the percentage of magnesium oxide, you can do 1.704105 divided by 2.65 to give you a final answer of 64.30586, or 64% to 2 sig figs. Based on the stem, we know it's 2 sig figs because we have 2, 2, 3, 3, 2, 2. So the smallest we have is 2 sig figs. And we leave it to 64%. Cool. Any questions on that back titration? It's always long. Would you go back to front for normal titration cues as well, or just back titration? Not always for titration, sometimes, but typically you don't really have to work through as many steps, so it's just chronological. and you know that the titration is going to be a back titration. That's a really good question. The way that you know is if you read something like this second paragraph. You know it's going to be back titration. Typically, if you're trying to find percentage purity, that's usually a giveaway that you're doing a back titration. And also, if you're weighing out a solid, so you're weighing out a solid here, and you're putting it into a massive concentration of the opposite substance, so like HCl for magnesium oxide, that's typically that step where you're adding in a solid and reacting off all of the solid with an excess amount of solution. That's usually your tell that it's a back titration. So watch out for that. And the percentage purity as well. Pat asks, can you please re-explain the concentration of HCl in the aliquot? Yes. So just stop me when it doesn't make sense, or shout out if you have a more specific question. But you'll know that the concentration in 25 mils that we found is going to be the same as the concentration for the 250 ml solution, because when you take an aliquot, you're just taking like a chunk of that solution out. So you're taking a chunk of the solution which will have the exact same concentration. Is that answering your question, or am I missing it, Pat? Okay. Aliquot mean a sample of. Aliquot means you're taking a small portion out of a larger solution and a specific volume. So a 25 ml aliquot is what we've taken here. Okay, cool. We'll move on in interest of time to get on to the final part of today. I know it's been quite rapid fire, but I want to make the most of the time we have. Final thing we'll talk on is buffers. Buffers are the one concept that I'll get asked about till the day of the HSC, as I tell all my students, and it's probably conceptually one of the hardest to understand. So try your best to get through this. One final question before we move on to buffers. The moles of the aliquot will be the same for 50 mils and 250 mils. I'll just paste this in the chat so everyone's not lost. When we talk about the 50 mil solution and the 50 mil solution versus the 250 mil solution, that's not an aliquot. The aliquot is the 25 mils that was taken from the 250 mils. That is an aliquot. But for the 50 mils versus 250 mils, the reason why these are not aliquots of each other in any way is because you performed a dilution. So when you add in solution or you add in liquid to the 50 mils, the concentration has changed. And this is not what would happen if you're taking an aliquot, which is taking a smaller part of the solution out. Here you have a dilution and the moles are the same because all you've done is add in water, if that's what you're asking as well. Is the answer to the previous question of the file? It's the answer to 29. Okay, cool. Back to buffers. So to finish off today, what you should take away from buffers, you should be able to, number one, define what a buffer is. Number two, write equations for buffers. Number three, talk about what happens when you add an acid. Number four, talk about what happens when you add a base, and relate both of these to why no pH change occurs. If you can do those four things for one buffer, you can do it for every other buffer that you'll come across. So for a buffer definition, it is a solution containing roughly equal concentrations of weak acid and its conjugate base, or vice versa. And the function of the buffer is that it can resist a significant change in pH when you add acid or base to it. Now, there's a limitation that when you add a certain amount of acid or base to the buffer, at some point you will consume all of the buffer and you'll have no buffer left. In other words, you've reached buffer capacity. So let's talk through an example here. Actually, I'll bring up one of the natural buffers. We'll do the blood buffer to make it a bit more applied. So the blood buffer has a pH around 7.35 to 7.45, where it maintains that pH. There are a few equations you can write for the blood buffer. Typically, it's going to involve bicarbonate and carbonic acid. So the buffer itself in blood is H2CO3 and HCO3 minus. And any buffer is defined by a conjugate pair of an acid, and a weak base. The two equations that are essential are these two. And for any buffer, you can represent them in pairs, as shown here, where you react either part with water to form hydronium or hydroxide. Okay. So to draw a graph, if you had this buffer in solution, your pH would start, let's say 7.4. What do we expect to happen if we add in an acid? What should happen to pH? It goes down. It does. Doesn't go down by much. I'll draw a few curves. Does it do this? Does it do this? Or does it do this? A, B, or C? A, B, or C? Okay. We've got mostly C's. It's definitely not A. A would be wrong because that's not showing what a buffer would do. There's no resistance there. That's if you had just like a strong acid in solution and you added base to it. Or sorry, you had this buffer in, no, you had a strong base in a very small concentration and you added in acid to it, you would just see the curve plummet. So then out of C and B, if you already have a buffer established where you have a bunch of H2CO3 and a bunch of HCO3 already, the buffer will already function from the moment you start adding acid. And so B isn't quite as correct as C in this case, as we see in the titration curves. What's going to happen is as you add acid, let's say you're adding in HCl, the HCl is going to interact with either of these equations. So we can use the second equation, for example. If we add HCl, that will push up the concentration of hydronium. So that's the change. How will the system act to resist this change? Good, we shift left. So we shift left, and that is going to push up carbonic acid, make some water, reduce our bicarbonate, and push back down our hydronium concentration. So once this has happened, what you need to do to lead your marker to what you're actually trying to prove, you're trying to prove that pH is not changing. So in your justification, you have to talk about the concentration of hydronium. Did it change or not? And if the initial change was that it went up and there was a resistance after that brought the concentration back down to very nearly where it began. So there's been a very tiny change, tiny increase of H3O plus concentration after all this resistance has happened. If that change was really small, therefore the pH change or the pH decrease is very minor. And that's what you're trying to do. You're trying to talk about, if I added acid, how would the buffer resist that change in accordance with LCP? And you would include an LCP definition in this, the first time you do it in this explanation. And you would say after the resistance occurs, the change was minute because of the resistance, and therefore pH decrease was very minor. And that's why the curve is flat or relatively flat in its decline. Eventually it will start to drop. And what point do we reach where we swap from going slowly to quite sharply? What point have we reached at this green line on the curve? Yes, your equivalence point, and in the context of buffers, we can also refer to it as, in the context of a buffer, it's also known as, yes, exhausted, the buffer's been exhausted, and we can also refer to that as buffer capacity. Or the buffer has been completely exhausted. And so you should also know that even though you can resist pH change using a buffer, at some point, the entire buffer will be consumed, meaning that beyond that point, there is no longer any resistance for pH change, and the remaining acid will just tank pH downwards. And you can do the same for explaining when you add a base through either of these equations, the flow is the same. You talk about if I added an acid, so if I added X, how that, what change in H3O plus or OH minus does it cause? How does the buffer resist? Tying in LCP. And finally, how does that affect either hydroxide concentration or H3O plus concentration overall, which will be a very small change. Therefore, pH small change. That's more or less the flow of your buffer response. Okay, any questions here? Any questions on buffers at all? Or is that clear for everyone? Three, two, one. Okay. So the final thing I'll give you, and we won't do it together just because we're a bit past 7. I know we always go over time, but you also have to learn how to do buffer calculations. There are 2 provided for you in the notes. And there's worked solutions underneath for how you go through those. But to very quickly address how a buffer calculation is done, there's one buffer calculation, sorry, here. You can tell it's a buffer calculation when you have a weak acid and its conjugate base or vice versa, and they tell you you have some amount of each. So here you have some ethanoate, you have some ethanoic acid. You're going to end up constructing an icebox where you have initial concentrations of both of those components of the buffer. And then you go and solve this as if it's a mod 5 style icebox. Small change assumption, and then go on to solve for X. But do have a go at that one if you're not too confident on buffer calculations. Otherwise, there's some more in the compendium, but Catalyst students, if you want to have a go at another buffer calc, page 256, there's quite a few towards the end. Have a look at those. Okay, but that brings us to the end of the topics we're going to cover today. I know I said we'd do another calculation, but I don't think it'd be worth just sending you off with a question without answers. So we'll probably wrap up here. As I said, Catalyst Chemistry, that's who we are. We teach online for your HC Chem about 3 to 4 weeks in advance. So for Mod 7, super heavy content-wise, it would be a great advantage if you walked into your week 1 class already having finished more than half of the module. And that's what you'd get if you come along with us for the next term. So that's more or less all for today. Hopefully you can make use of the notes and the Discord as well. But if we don't see you again, we'll see you when we see you. And if we do see more of you in the near future, look forward to working together. That's all for today. Enjoy your evenings, and I'll stay behind for a few questions. Okay. Do we get access to the harder trial questions? Unfortunately not. That's only for Catalyst students. But you'll get access to the titration questions if you leave a comment on some of our Instagram posts about titration. Go look at those. The recording will go up on YouTube later tonight. Are we allowed to use Henderson Hasselbalch in the HSC? I would not recommend it. I don't think it's supposed to be used unless you're given the equation to work with. Can you buy our resources? You can send us a inquiry on the website. We can tell you more about the resources. We do offer them. Just have to send us a inquiry. I wouldn't use a Henderson Hasselback, so Farhan. I would try avoid it. Would you always state small change assumption for every icebox? Absolutely. If you don't state it, you may lose marks, and I would not want you to lose marks on something that you've done correctly. Yes, the recording will go up on YouTube, and you can watch it back anytime, I guess, before your exam. Okay. 29 of us still here. Any questions? If not, we'll wrap up. No worries at all. Hopefully that was valuable for you guys. See you, everyone. Enjoy your evenings. Alrighty. I'll wrap up the Zoom now. See you in the next one, or see you online somewhere. See ya.